Yes, yes. So now we have 15 seconds, approximately. Yeah, should be running now.
Good.
So that's good. So welcome again to everybody. We're gonna run almost on time our keynote lectures. Our first lecture will be done by Fabian Scheurer, who's the director of Design to Production. Fabian, we'll leave you the stage for 30 to 35 minutes talk. If Jenny is in the audience, she could come on the stage and we will arrange her talk that will come just next. Fabian, it's all yours.
Wonderful. Thank you very much indeed. I'm happy to be in Paris, more or less. Thank you very much for the invitation. I'm very honored to be given the chance of giving a keynote this afternoon. Welcome to everyone here. Unfortunately, I can only see your avatars. There might be a few familiar faces in there, but maybe we'll have a chat afterwards. I'll be talking about building better models today. I've seen a few of the presentations of the conference, and there is fantastic work to be seen on architectural geometry and digital modeling. I wanted to sort of divert a bit from this path and not talk too much about geometry, but talk about sort of the underlying things that happen there. So as an introductory part, let me sort of introduce myself and what I'm doing or what I have been doing for the past few years. Some of you might know that Design to Production is in business since about 2007 as a spin-off of ETH that I founded together with partners. And we were behind of a few very interesting, very curvy projects, some of them also in France, like the Centre Pompidou in Metz by Shigeru Ban that was opened in 2010, where we worked for the timber contractor Holzbau Ammann to get this roof fabricated. Then we had the honor of working together with Simona, a French timber contractor, on the French pavilion for the Expo in Milan in 2015. You can see a little bit of the curvy stuff inside of the pavilion here already. We have one wonderful project in Paris, which is the Scène Musicale on the Ile Séguin, also by Shigeru Ban again, where you can see it's a concert hall with about 1,500 seats, I think, with a wooden grid shell around it that holds the glass facade. We also had the chance to build a mosque together with timber contractor Blumer Lehmann for Mark Barfield Architects in the UK, in Cambridge. That was opened in 2019. And our last big project, maybe biggest project that we worked on so far, is the Swatch headquarters in the Swiss city of Biel. That was open 2019. Again, the Shigeru Ban project. Again, the timber structure, a pretty big one. I'm going to show you a few more images right away. It's a almost 250 meter long timber grid shell that goes around the bend and then takes off, goes over a street and rests its head on the other side of the street on another building, which is the Omega 2 building, about 34 meters wide at the highest point, almost 30 meters high. And that was one of the very few projects where we had the chance of working in the project rather early together with the architects and the client. Very often our projects are sort of based on our work being directly contracted by the timber or any other contractor that is then taking over things after tender and realizing. Swatch has about 2,800 bespoke facade elements of different types. It's actually an office building. There's a 4-story concrete structure inside that is wrapped into this facade, which is based on a timber grid shell that is put together from about 4,600 glue lamp parts that were prefabricated digitally and then put together on site in the 4 layers crisscrossing each other. Our role in those projects typically is exactly what our name is saying. We're doing neither design nor do we do any production. We're just doing the two in the middle, which means we're translating between design and production, making things buildable in the end and provide data for the production. To do so, we of course also try to inform design about production, at least as long as we are in a project like Swatch, where we can influence the design a little bit. So the story that we're telling is that design to production speaks both design and production, and we can more or less translate simultaneously from one side to the other. And we're doing this based on digital information, so we're placing basically both sides, design and production, on digital models. We've been in business since 2007, actually a bit longer, because we had the chance of working at ETH Zurich for a couple of years. And we teamed up with Arnold Walz, who was an architect in Stuttgart, who has already worked pre-2007 on large-scale projects like the Mercedes-Benz Museum and others. So this is sort of a wrap-up of the probably most and least famous projects that we've done over the last 15 years almost. They are 100% prefab. They are 100% digital. 80% of them are timber, which is more or less an accident because it wasn't planned like this in the beginning, and almost all of them are free form. Why is that? We think that offsite prefabrication is great because we want to get complexity away from the site, especially when it comes to those complex geometries that you've been talking about for the last 3 days. You can see here sort of the single parts of the Centre Pompidou as they were fabricated in the Black Forest by Holzbau Ammann. And on the right-hand side, on site, where they were stacked on top of each other in 6 layers in Metz. And you can imagine that you don't want to measure and do things on this roof, especially when the weather is not as fine as in this picture. You want to put things together as quick as possible. And this is exactly what we think is actually a good way of working. We want to get complexity away from the site. We want to embed the complexity into the parts. So the part itself basically already defines where it goes to and what the geometry of the overall structure in the end should be. We do this 100% with digital mass customization and parametric modeling because actually there's no other way. You don't want to do models like the one on the left-hand side, which is a close-up of the model for the French Pavilion in Milan. You do not want to do all those drilling holes by hand. You don't want to model them. You want to have parametrics doing that. And you do not want to carve those curvy beams out of a glue laminated blank by hand. You need digital fabrication equipment to do that. So basically what we're exploiting is the idea that we have a machine that doesn't care if it's doing 1,000 different or 1,000 similar parts, as long as it gets the right information in form of the right digital data to drive it. We are doing about 80% timber project because it turned out to make sense. Design to production was material agnostic from the start, if you like. But it turned out that timber is actually a great project for what we had in mind. We have BIM and VDC. Everybody talks about digital models. Everybody talks about more industrialized building and getting more performance into the building process as such by exploiting principles like lean prefabrication, mass customization, and having proper quality management going on. And then we have a great raw material, timber, which is sustainable and which is actually pretty far advanced when it comes to digital fabrication, at least in Central Europe, where in most of the bigger timber carpentries, there is already digitally controlled fabrication equipment by now. Typically, they're doing straight things with that, but there's a few that push the envelope a little bit and want to do curvy, crazy things. And we quite deliberately ended up in the middle of all this and thought, now the time is ripe for doing more of digital mass customized timber projects. Up to now, that was almost only freeform, but we sort of challenged that a bit and tried to get for everything that we learned over the last 15 years in the curvy, crazy Formula One project business onto the road, if you like, and put that also into square buildings, which is a challenge that we deliberately took because we thought they should be sort of all right by now, because also there's BIM out there. Everybody does digital models, not everybody, but sort of on the rise. That there's digital models on the planning side also of rectilinear buildings. We know that timber is already digital. So the idea was to take a project, and this was the House Crocodile, named after a famous Swiss locomotive engine. It's in Winterthur, which is 30 minutes outside of Zurich. It's a completely square building, except for the little roof that you can see up there. A housing block with 254 apartments on up to 8 stories. And we thought, since we've done it a couple of times on the curvy side of things, we could use a BIM model that was done by the architects and the engineers in the planning stage. We could take that over on behalf of the timber contractor, which was Implenia Holzbau, pull off our magic of parametric detailing, and then hand over fabrication data to digital prefabrication at Implenia. And I have to say, it utterly failed for a number of reasons that were pretty hard to foresee from our side. But after sort of thinking about what happened there, I mean, it failed completely because you've seen the images, the building is there, but it failed pretty completely in terms of exploiting productivity gains by parametric detailing and prefabrication there. So there was a lot of manual work involved. And in the hindsight of this project, we found out a lot of things that we sort of intuitively did differently from everyone else in the curvy projects the last 15 years. And this is basically what I'll be talking about for the remainder of this session here. The question is, why do most digital building models not serve the purpose for digital fabrication? Basically, they're not ripe for digital fabrication, but actually, this is what I'm going to show, is they're ripe for disposal mostly. Everyone who's ever been in a presentation on building information modeling has probably seen this infamous diagram, which is attributed to Patrick McLeamy, who actually did not invent it, but stole it from somewhere else, but it's still out there. It shows you the effort or effect of planning over time and the different planning stages. What you see in the middle, the big black curve, is the traditional design process where you have the biggest effort in this bell curve in the construction documentation stage before it goes over to the contractor and then gets built. What you also see is a curve, which is the red dotted curve that goes up exponentially to the right-hand side. That is the cost of design changes. Pretty obvious, the later the change comes, the more costly it gets. And on the other hand, you see the effect of design changes in dotted black, which is asymptotical to the right-hand side. Also pretty obvious, the later the change comes, the less effect you can have it. And the whole idea behind building information modeling, according to Patrick McLeamy, is, hey, we're building a digital twin before we actually start building. We shift the effort forward in time, test everything that we need to test, and then hand over proper coordinated digital fabrication data or data to the other side. And the question here is, what is actually underneath those two bell curves? Is it just the same thing, only early in time? Which would, of course, result in us just being in the same trouble 6 months earlier than before, which is probably not the desired effect that the whole digitalization in the AEC industry should have. Or to put it with the words of Thorsten Dirks, who is the CEO of Telefonica, who gave an interview a couple of years ago and coined the term, when you digitalize a shitty process, what you get is a shitty digitalized process. And this, for the bigger part, has been happening from our point of view in the building industry in the last few years. Because we have a few other things that we need to consider when it comes to prefabricated, digitally prefabricated timber structures in this case. Prefabrication requires a lot more coordination than if you do things on site. Luckily, the timber guys are actually pretty used to prefabrication. All the carpenters always have done the detailing on the roof trusses on the ground before they hoisted them up into some church roof. So on the execution side, the mindset is basically already there. Also, what you have in a project like Swatch is you have a lot of coordination with other trades to do. On the right-hand side, you see a view into the ceiling of Swatch and just a few of the installations that happen up there in the crisscrossing beams. So what you need is you need to be sure that the things that you prefabricate offsite actually fit together, which you can see on the left-hand side. One of the parts is dangling up there. It's a small one. It's only 2 meters long. There's parts up to 12 meters in the structure. And you need to be pretty sure that everybody who comes after you and wants to basically pull a thread or a pipe through the structure finds a hole for that. And what we need to do more in projects like this is what's called design for manufacturing assembly. It's something that has been invented in the 1980s in the consumer products side of things. In product design, our role models basically, and this is sort of a coincidence, are Swatch, who managed to save the Swiss watch industry by reducing the number of parts to assemble in one of those watches that you can see here from around 100 down to 51 and save a lot of time and money. To do that, this is why Swatch watches are so cheap, because you can integrate a lot of the functions into this plastic housing that you see there. Clever thinking, yeah, but was only possible then after the industry was able to fabricate those housings with the needed precision. And on the other hand is a famous Swedish shelf that is in the market also for more than 40 years now. That hasn't changed on the outside very much, but if you have had the chance to build a few of those over the last years, you might have recognized that the detailing has changed over the years. So from every series to the next, the guys at IKEA invested a little bit more thinking into making smarter details so that people like you and me cannot fail anymore putting those things together. And then we don't block the hotline and ask stupid questions about how to put this thing together. And this is basically what we're doing on larger projects. We're trying to make smart detailing that is easy to manufacture and easy to assemble. Unfortunately, what we realize in the building industry is that many of the planning processes still follow the so-called waterfall model. So if you have a process that needs to look into a series of different topics, which is the sort of y-axis on the left-hand side, over a series of project stages or over time, this is the t-axis. Basically, you drill down deeper the further you get, which leads to the not so good result that you start talking about fabrication and assembly only once you've reached detailing and production planning stage of the project, which is not good if you're trying to basically do product development on an assembly kit like an IKEA shelf. You need to have fabrication and assembly in mind a bit before. So the interesting topics come to light. Another thing that actually we realized during the Crocodile project only is that building information modeling cares a lot about parts. So you have intricate models like on the right-hand side where every part has a lot of information, but it does not care at all about details. So basically what you cannot find is if you have different window details, which detail actually goes where. The only thing that you see is the outcome. So which parts come out of it, but not what happens where. There's no way of actually having typed detailing and finding those details from the engineer's catalog on the left-hand side in the model on the right-hand side, simply by sort of design or misdesign of building information modeling. There's no way of having typed details in the model. The other thing that happens when you talk about digital fabrication is that it requires a complete, correct, and precise data in the end. So you have a CNC machine which is perfectly capable of driving a 20 centimeter long tool through a 12-meter long beam with a tolerance of less than 0.5 of a millimeter. And this is not just because we are Swiss and we want to have it precise. This is because what you want to do is you want to do all the detailing already directly on this machine. And if you have intricate detailing with steel dowels or pre-drilled holes for screws or whatever, your engineer is going to tell you that they have to be within a certain tolerance to be actually then ticked off in the end and approved. So the machines are capable of doing very precise work, which means that they will reproduce every kink in the digital model that is bigger than the production tolerance of 0.5 of a millimeter duly in the material. And now the question is, how do you get from a schematic design early sketch model to a crisp and sharp and correct and precise fabrication model at the end of the process in one go? Because this is a bit the promise of building information modeling. Here, you set up a model and then you send it over to the fabricator. Right? But how do you get from this 6B sketch on the left-hand side to the 6H production data on the right-hand side in one go? The answer is you don't. The state of the art pretty much is you model whatever you have, then you throw it over the fence to the fabricator in the 10th stage, and then the fabricator looks at your BIM model and can't really decide which parts are precise, which parts are complete, which parts are correct. And since he cannot really trust what's going on, he's basically probably dumping the whole model and remodeling the thing from scratch to have a model that he can trust drives his machine at the right locations in the material. So what you get is this little diagram that I found in a book by Andre Bormann in 2015 that shows you the rising project knowledge over the time of the project stages from left to right. That would be the black curve. And after every stage, the amount of digital information that is actually available for the project sharply drops almost to zero, because the models that are produced in the earlier stage are actually not really usable in the later stage, mostly because there's too much information and too little quality. And our hypothesis there is that this is at least partly due to unclear objectives. So the guys building those models early on in the project cannot really be blamed because they are not told where their models are actually supposed to end up. So the objective of the model is not really clearly defined. So we do what we do all the time, we build models. So the question is, how do we rethink our methods to create usable digital tools? And the first thing that I would sort of come up with is the term of lean modeling. Essentially, all models are wrong, but some are useful, is a quote by George Box. And the idea behind that is, what is a model? A model is a simplified reproduction of reality. That means whenever we find reality to be too complex to actually handle or grasp, we start building models to test hypotheses, to document what we've been thinking of in the planning stage or whatever. A model is always simplified, which brings us to the sort of repetitive question during modeling: what is it that we put in the model and what do we leave out of the model? We need to be aware that only a simple model is a good model. Yeah? Think of Marie Kondo, the famous Japanese lady that cleans up other people's wardrobes. The question that is recurring all the time is, do you still need this, or can we dump it? And the same holds true for models. A good model is as simple as possible, but to decide what goes in the model and what stays out of the model, you need to know about the purpose of the model pretty precisely, actually. So here you see two models of the Swatch building that actually show almost the same thing. This is the part of the reference model on the left-hand side in 3D, which shows you the different types of facade elements that are lying between the beam grid on the surface. And since we didn't have a chance to see all those elements at one glance from any perspective of the project, we generated a second model, which is the one on the right-hand side, which is actually a dual model of the left-hand one. It's the facade flattened out on the ground. It's a purely topological model where you can see all the facade elements and the types and the numbers and a lot of other information on a flat drawing, if you like. But it's more than a drawing. It's really a model. So the two models actually correspond with each other, and changes in one model are reflected in the other model and vice versa. So we could put the right-hand model on the table basically in meetings and coordinate with the facade engineer, with the MEP engineer and all the others. What we would do and how we would shift element types back and forth. And then the same afternoon, reflect the whole thing in our other model. And this is exactly two models built to purpose, because there's a lot of things left out in both of them. But they are as small and as slim as possible. So the idea would be small is beautiful and wanted is meaningful. We're always talking about lean production when it comes to industrialization, which means we are thinking things from the back-end side. We do not just push down things, the production process, and then they're waiting until the next station that does something with them has some spare time and actually takes them and uses them. But we are delivering just in time, and the back end of the process is actually pulling from the front end. This is pretty normal in industrial fabrication. This is also pretty normal in digital prefabrication building, but it's not really normal yet in the modeling side of things. We still push down multi-purpose shotgun models without a clear objective through the planning process, instead of building purpose-driven and decluttered models that are pulled from the fabrication side. Comes back to the question that we had before: where do we actually want to end up with all the digital data that we are preparing now? The second thing that I want to stress is that we need to think about more agile ways of modeling. A working design is the primary measure of progress, is a quote from the Agile Manifesto, which actually comes from the software development and was a big movement that went away from the good old waterfall model in software development also, for the better idea of actually trying to do much smaller cycles in project development that always end up with a working piece of software. Now in the building industry, we cannot have smaller buildings that are working throughout the planning project until we have a bigger building at the end. But on the modeling side, this works very well, actually. So instead of using this waterfall model, we agree that prefabrication actually is product development, and we cannot wait to discuss assembly later on in the project. Okay? To give you an example from Swatch, we have about 2,600 of those crossing nodes in the Swatch grid shell, where at every point we have 2 beams crossing. In every direction there's 2 beam levels. So we have 4 beam levels crossing at every node, every 2 meters basically. The idea of Scheurer and the engineers was to have lap joints at the crossing, because the beams should be basically crossing at the same level. Right-hand side is the original drawing from the engineer. A bit hard to understand, but you will do in the next slide. The classical half lap joint from carpentry is well known. You have 2 crossing beams, you take away half the cross section on every beam, and then you put them back together. Bang, there you are. And in Swatch, we don't have 2 of those beams crossing. Actually, we have 2 levels stacked on top of each other. So we have 4 beam levels crossing there. The problem with this half lap joint is, how do you engage the 2 parts into each other? There's one vector that is perpendicular to both beams, and that's the only direction that you can move the moving part into the fixed part. Unfortunately, if you look on the right-hand side, we have curved beams in the Swatch grid shell. So we have 5 or 6 lap joints along this curved beam there. This, by the way, is the project manager of Scheurer, Taro Okabe, looking at the beam there that just arrived on site. So you have a curved beam, and all the lap joints on this beam are actually pointing in different directions. Slightly different, but still. So you couldn't use a standard lap joint to do that, and we had to invent pretty early on a solution for this grid shell that would allow us to keep the idea of having those double lap joints, but on curved beams. And the idea is to have what we call the skewed lap joint, where there's a few corners missing. And now you see why the cutouts on the right-hand beam in the image look so strange. We're cutting away a few corners, which allows us to engage those lap joints slightly from the side at a maximum defined angle. Yeah, and those cut-off corners will be visible in the end afterwards, which leads to discussion with the design architect, of course, but in the end, he accepts it as a design feature and not as a bug. Yeah? What you can do early on in the project, if you found out about that, if you have a proper model, you can, of course, do a search over all the 3,400 nodes that you have in the model and find the worst cases. So what would be the opening angle of this lap joint that you really need? Because that is, again, then really important information for the structural engineer, who wants you to cut as little material away as possible because he needs it for the structural integrity of the structure. And then the negotiation process goes on. So what we had is we had a very simple model of this structure, where only the beam axis and a placeholder for the joints was in, and you can see here on the left-hand side. It's basically only the axis that you can see, which served as the basis for evaluations there. And once we knew what was going on, we could feed that back into the model and define the opening angles for the different joints there. And this is what it looks like in the end in the workshop. So there's 2 beam halves put together on the left-hand image without the crossing beam, and on the right-hand side you see the crossing beam going through the hole in the middle. So the idea is we want to have what's in the software industry called Agile development. We want to have a feasible solution after each cycle. And we want to drill this feasibility study down to fabrication assembly and also to maintenance at every stage. Because if we want to do prefabrication, we need to do. Yeah. So the good old waterfall model is not working anymore. We need to come up with a different model that can drill deep at every stage, but then also doesn't necessarily stay down there and suddenly starts doing all the detailing already in the first concept stage, but resurfaces to the appropriate flight level of abstraction in the process. It puts all the results that came out of those questions that we posed while going down the loop into a reference model or a coordination model or whatever when we come up again. I've already said we're stupid. No, we're not stupid. We're lazy but smart. Yeah? And we want to make things, or we want to delegate things to computers. So we have to come up with rather systematic approaches of what's going on and put that in parametric modeling. And that can go terribly wrong. If you look at the crocodile house that I showed you beforehand, that was pretty different because we had 254 apartments. And for those 250 something apartments, we had 92 different window details. On the right-hand side, you see an explosion of one of the wall elements in this project there. And that is not what you're looking for if you want to do parametric detailing. On the other hand, we had the Swatch headquarters. We had about 2,800 bespoke facade elements, and we only had 10 parametric types. So we had to solve it once. On the right-hand side, you see 1 out of 470 glass panels that have a cold bent glass, single glass panel on the outside and a triple glass panel on the inside, a curved timber frame in the middle to hold everything together and define the shape, a shading device, a few aluminium profiles, and so on and so forth. There's a lot of nitty-gritty detailing there, but basically it's all parametric. So we have one parametric type that serves the purpose of generating 470 different models for glass panels that are then given into digital fabrication. And since we have a fully functional office facade, we also have 20 kilometers of pipes and trays and heating and cooling panels up there. They're all bespoke. So we have, in the end, about 75,000 bespoke parts in this timber grid shell. And we managed to only arrive at 11 wrong parts on site, which is also due to parametric modeling, because typically what you do is you write the parametrics to do the planning. You do quite a bit of testing in the beginning. And once it comes out good on the first 1, 2, 3 parts, and you pick the worst cases, of course, then you can be pretty sure that all the others arrive on site also. Yeah? Sometimes stupid things happen. And we ended up with about 0.14% of wrong parts that ended up, which is pretty good for a structure like that, and was much worse on the side of the crocodile, where we had many manual details to do. And manual mistakes happen all the time. So what we want to do is we want to systematically create detailed models from abstract models, and we want to generate them. And this is where you already can see, oh, we don't have models that are thrown away after every stage, but we have models that are actually consistent there, because then we can use them for as an input for parametric modeling. And this is what we call multi-scalar modeling. When in doubt, about. The problem with those waterfall models is typically what you do is you have an abstract model with less details, and then you create a more detailed model for the next stage and neglect the old abstract model. Yeah, basically, it's not looked at anymore because it's already outdated. It doesn't get updated because all the information plus a little bit extra is in the next model, which makes it extremely hard to backtrack. If you realize that you made a mistake, even if you use the parametric model to create a more detailed model, you cannot backtrack anymore because the old model is outdated. Also, what you have is you have growing model sizes at every stage. And that leads to the typical situation where you ask someone to send you this and that information in the late project stage, and you get 4 gigabytes of IFC data with everything in there. And then you start searching. It's not really feasible. It doesn't make any sense, because what you need is a few Bmaxes or whatever. So why giving over all the other things that you need? The answer is, in a waterfall process, you can't do, because there is no abstract model anymore. So what we try to do is we put a stack of persistent complementing models on top of each other. They have different names, they have different purposes, and that's the important part, they have different levels of influence. So everything that basically defines the building is in the reference model. And the deeper you get, the more local the changes get in the models, which is different from what you see out there as BIM models, because typically you have one big thing there that you can sort and that you can search, but you never really can take apart and get a more abstract view on the same project again. Good thing is, of course, then we can generate the more detailed stage from the abstract stage at any given point, and we can repeat that. So should it turn out to be wrong in a later stage, we can update the reference model and repeat that step because we still have it. So coming to the conclusion at the end, why the tail of the process needs to wag the dog. What we see is digitalization also in the building industry is the answer. But what was the question again? We think that digital mass customized lean offsite prefabrication could turn the building into an actual industry, because up to now it's mainly craftsmanship, to be honest. Yeah? There's a lot of things solved ad hoc on site, which has nothing to do with industrialized processes. Industrialized processes are happening in a controlled environment with the proper quality management. Like we can see here on the right-hand side, where timber modules are prefabricated at Blumer Lehmann site in Switzerland, or when you have prefabricated, fully installed facade elements coming out of the factory and being installed on site. Like on the left-hand side, this is one of the walls of the Crocodile project. The problem that we have is actually upstream. The planning does not deliver for the new production facilities that we have. Not that we still have those guys in their white coats at the drawing boards, but basically they just have been replaced by BIM models that are still aiming at the same objective in the end. They're delivering 2D drawings to the execution side of things. They're not built for delivering 3D modeling data that is to be used in digital fabrication at the end. And this is the point that we need to tackle, and we need to tackle that urgently, because this is where all those good ideas of having prefab mass timber projects going on are stuck at the moment. The production side is already there. The equipment is already there. The people that run the equipment is already there, and they're desperately waiting for proper input coming out of the planning stage. And that means we need to rethink how we deliver models to the fabrication side of things. And that brings me back to the original question. This is all our projects, and as I say, 99% of them are freeform, crazy, curvy Formula One projects. So why only crazy projects? The answer to this question always is A, because we can, and it's a lot of fun, and it's great. And you all know this because you're here at AAG, and the whole topic is architectural geometry and the crazy side of things often, and how you make it feasible, how you make it producible, how you describe it as easy as possible, and then materialize it to get the bits across the gap and turn them into atoms. So because we can is always the first answer that we give. The second answer is because actually all those freeform projects are the low-hanging fruit. Because if you have a project like this, everybody's already at the tip of their toes very early on in the project. They know that they cannot handle this with the standard processes that they usually use. And you have an easy time convincing them that you probably should change one or two things in the process. In a standard project, there's always someone coming up saying, nah, we've done it like this all the time, so why change anything? And this is basically why we've only done crazy curvy projects over the years. The aim, of course, is a different one. The aim is really to get this from the Formula One onto the road and start the digital revolution in AEC. Yeah? But then we also need to discuss how we actually want to get information down the chain to the fabrication, and the other way around. Fabrication actually needs to define how they want their information being handed down. So, and this is the title of the talk, the tail needs to start wagging the dog. thank you very much, and I'm looking forward to discussion.
Thank you very much, Fabian, and I think it was an extremely interesting talk. I have some questions, but maybe Cyril, do you have question from YouTube live? And
yeah, well, just let me refresh a little bit. There is actually one remark on you remark and on YouTube, yes, and the question is about to what extent you think that this now innovative methods can be extended to mass customization, so you just extended to more to mass production, or mass
Yeah, I think that mass customization is the actual trick in everything that we're doing. It's pretty obvious in the curvy projects because you see that all the beams in the swatch grid shell are different, even though they're following the same rules. So they're all based on the same parametrics, and this is what mass customization actually is about. If you look at an orthogonal project like this crocodile housing building, it seems like there's a lot of similar things in there. But if you look closer, you will probably find only 1 or 2 or 3 wall elements that are actually the same. They are basically mass customized. So they're all slightly different due to various reasons. And the whole trick is basically to come up with the right rules for this mass customization, which is surprisingly much more difficult in orthogonal projects than it is in curvy projects. But in the end, it is about developing like an IKEA shelf product system that can be put together.
Okay. Yeah, one more from Romain Menil. It is more related to geometry. So given your experience in digital fabrication and mass customization, do you think that repetition of components in free-form structure is still a viable optimization goal?
It can be. It depends on the project and it depends on the fabrication. Typically, we realize that in those free-form structures, on the planning side, it's much more effort to find similar parts in a non-similar structure than to simply come up with a production chain that exploits the capabilities of digital manufacturing and produces bespoke parts. At some points, it makes sense to find similar parts. For example, when fabrication of material is depending on jigs or on molds that can be reused, for example. So it's always a trade-off. If you can mill the things right out of the block and the machine doesn't care, it doesn't make sense to find similar things. And if the production process requires it, it can make absolute sense to and search for optimization there.
Okay, and the repetition of connections makes sense also, or is it more? I think it's more target. You have to try have a repetitive connection system rather than repetitive members.
The interesting thing is if you have a complex structure, basically it's very hard to get the complexity out of the structure. What you can do is you can shift it from the part into the detail or from the detail into the part, but it still is complex there. So we've had that where you try to sort of rationalize things down to single curved beams, for example, but then you get more complex nodes than in Torch and vice versa. So it's a trade-off, basically.
Yeah, sure.
Yeah, I think there's a Ricardo, I think, who's on the stage. Maybe he wants to ask a question.
Yeah, hi.
Hi.
So about, well, I had a question, but also I wanted to say something about what you were just saying. As far as I understood from your really, really interesting presentation, that instead of repeating parts, you have a repeating detail of a complex system. So you only have this single detail of the window, let's say, within the whole structure, and on the Shigeru project, and then on the Lion House project, you had, I don't know how many hundreds of details of all the different windows, which in principle are simple surfaces but complicated connections. So that's what makes the whole difficulty of the project explode, as far as I understood it, because even when every component will be different on the Shigeru project, they are all following one rule, let's say, or one set of rules, and they are all compliant to one detail. So
Yes.
I think that's the main takeaway, is it? And now the question was, it's also very interesting how you can put such detail and such art in the beam itself, because normally in the steel industry, the node has all the art of the structure, let's say, because you have straight beams, and then the node takes all the information of the surface in order to accomplish the discretized surface. So how far do you think is then steel production from wood production in order to accomplish the same level of detail? Because I know from steel is many times exponentially more expensive to make it on such a complicated beam, and it seems to me with wood is working really nice. So yeah, do you have any insights for the steel? How far do you see the progress?
I think that's one of the big opportunities of timber, that its machinability allows to have rather complex geometry directly fabricated out of the beam. So you can bend beams as you can bend steel, and you always have the same problems, that it springs back and is never precise. But as opposed to steel, you can put a curved timber glue-lamp blank onto a CNC machine and then basically just mill away the excess material within 0.5 millimeter tolerance, including all the details. And that's going to be hard with steel beams for the foreseeable future, I would say. So the question would be, is it possible to come up with sort of more complex members in steel by not using standard profiles, for example? And there's a lot of work with curved folding out there, for example. There's a lot of work with automated welding of box beams and stuff like that, where you could come up with more complex geometries by changing the fabrication method of the beam. But you clearly identified one of the big differences between steel and timber structures when it comes to members. Timber members can be of much more geometric complexity than steel members at the moment, probably.
Okay, and one last question. So when you have the joints between the timber elements, they are mostly steel parts, as far as I understand it. They are more or less standardized joints, or is it that also every joint is, let's say, its own sculpture, as I will put it?
Depends on the project. In Swatch, actually, there's very little steel in those cross joints. It's a timber joint. There's screws in there, which is easy because you have to pre-drill a few holes, and then the guys on site have to just find the hole and the right screw and put it in. There's very little steel parts in there, and that's generally also the idea, to have, if there's steel parts in there, that the steel parts are as similar as possible, and that the sort of deviation geometry is taken by the timber part, which is on a CNC machine anyways. So typically what, for example, happens is that if you have an angled steel part at a connection, you create different types of steel parts with 5, 10, 15 degrees angle, and remaining plus minus 2.5 degrees of angle are taken on the timber side of things, which makes it easier.
Yeah, of course. So making these steps, that makes a lot of sense. That's very enlightening. So mostly, I guess, is the supports, the connections that are still, as far as I saw from the images. But anyway, thank you very much. I think you echoed a lot of the sentiment from the steel and glass industry also. This workflow and the way the information flows, I think is also a very big bureaucratic challenge, but it's very nice to see more people acknowledging this. Thank you a lot.
Thanks for the feedback.
Thank you. Just maybe I'd like to ask a question. Just don't you think also that geometry and tool we use for geometry could be also part of the problem? You see, now most of the design tools that are used for design geometry are NURBS. NURB surfaces don't have any good properties or constructive properties. If you put a mesh on a NURB surface, it won't have any property of nodes without torsion and all these things. And don't you think that people are not enough aware of using good surfaces that are naturally buildable? Because isn't it maybe the roots of the problem? You know that if you build surfaces like constant mean curvature surfaces, they will naturally give you a network of beams that don't have torsion and flat panels and all these things. What do you think?
I think the challenge is to have the designing part being informed about what's possible on the fabrication side of things. This is the main challenge. And I've seen lots of great work also at AAG. I mean, all the work of Helmut Pottmann basically comes from the idea that we want to use flat glass panels. Yeah? This is fabrication information flowing forward in the process and finally leading to a mathematician coming up with ideas how those things could be tackled on a theoretically sound basis. And I think there's a lot of other problems out there that still need to be solved when it comes to producing complex geometries. And I think is a giving and taking all the time. Yeah, there's sort of one of the problems gets solved. Someone comes up with a new fabrication method, and we have a new stack of problems for the next AAG probably. So I think the important thing is to realize that those two things are interconnected and depend on each other. And then it doesn't really make sense to come up with a perfect theoretical geometry solution on one hand side, and no one's asking for it on the implementation side, and vice versa.
Okay, thank you. Cyril, do you have any question from the network or?
So let me check again. I reload the page.
Well, anyway, I think we might have gone a bit too long. Just yes. Maybe as a final question, quite a few of us are also professors in the School of Architecture. What would you say to architecture students to be compatible with the numerical tools that will actually make their designs?
Numerical tools in terms of designing or in terms of fabricating things?
I think it's the entire process. When they draw something, what you should, well, what is the advice when they start to draw something, what they should think about?
I think,
there we go.
Jenny. I think the best thing they can do is get their hands dirty during studies and try to build things, because then you suddenly get a quite good impression about what the actual questions are in product design, if you like, of things like that. And the other good advice might be fail as good as possible while you're still studying, because that's the thing that you can do there. The more mistakes you make, the better, because later on it's going to be really expensive.
Okay. So it's a nice conclusion. So thanks again for your presentation. That was wonderful.
Thank you very much for having me. And if there's more questions, please feel free to write emails. I think the address was on the last slide.
Yeah, okay. And if you stay among us at the beginning of the afternoon and you go on the map, you can have informal discussion with people.
Great. But first I want to hear Jenny.
Yeah. Yeah. Now it's the turn of Jenny Sabin. We're really happy to have you. We saw you having trouble getting into the Jitsi conversation, but now it works and we're really happy. So as we're running slightly late, maybe we can go straight to your keynote. So Jenny Sabin is a professor at Cornell University, and she's director of the lab, Jenny Sabin Lab, I think. And Jenny, try to share your screen, and the stage is all yours.
All right, thank you so much.
It's on the lower part of the screen, lower left, normally.
Yep. Okay.
Yeah. Yes, yeah.
Can you see that full screen?
Perfect.
Excellent. All right. Well, thank you so much for the invitation to deliver a keynote at AAG 2020. It's my sincere pleasure to be here this afternoon. The title of my talk is Biosynthetic Architecture, Transdisciplinary Design Research. An unfortunately well-known fact, and according to the World Green Building Council, building and construction account for 39% of annual global carbon emissions. The heating, lighting, and cooling of buildings accounts for 28% of this total, and the remaining 11% comes from what is known as embodied emissions, or upfront carbon associated with materials, construction, and building processes throughout the building's life cycle. The energy intensity per square meter of the global building sector must improve on average by 30% by 2030 to meet international climate ambitions set in the Paris Agreement. The COVID-19 crisis is forcing a reconsideration of workspaces and residences and other occupied structures, such as the studios and spaces that we teach in, as well as products and supply chains, as these crises reveal systemic issues of diversity, equity, and inclusion. Radical new models are needed for design research and collaboration across disciplines to address these issues and questions. One approach entails the hybridization of labs and studios to fuse innovations across science and design to generate next-generation building materials and structures that are adaptive, efficient, smart, and importantly, resilient. My keynote talk describes ongoing projects in my lab at Cornell University and projects emanating from my practice, Jenny Sabin Studio, that integrate biosynthetic design processes and the dynamics of light and energy as design drivers to innovate responsive, non-standard photovoltaic building skins, biobricks and tiles, and sentient spaces. We ask, how might buildings behave more like organisms, responding to and adapting to their built environments? We frequently start with very simple parts and rules that, through feedback and iteration, engaging a bottom-up design process to produce much more complex spatial wholes. This interest probes the productive tinkering and misuse of digital fabrication machines frequently found in alternate industries, including textiles and the automotive industry. Importantly, these questions and topics are informed by issues of craft and making to produce bio-inspired material systems and software design tools that have the capacity to facilitate embedded expressions in our built environment. In the not so distant future, materials will not just be elements and things in buildings, they will generate immersive spaces, acting upon and responding to affordances in our built environments. Like the cells in our bodies, sensors and imagers will learn and adapt, making materials not only smart, but also aware, sensate, and beautiful. We will be able to tune our spaces to personalize architecture. A seminal reference for my work is the biological extracellular matrix, which is a dynamic protein network that physically and chemically couples the exterior environment of cells with their interior and vice versa. This matrix environment is a cell-derived woven and globular protein network that contacts most cells within the body, an architectural textile of sorts. Importantly, as I have learned from my longtime collaboration with Dr. Peter Lloyd-Jones and initially through our co-founded hybrid research and design unit, Lab Studio, this environment changes dynamically throughout development and disease. And we are specifically interested in models that show how these alterations feed back to control cell and tissue behavior at the level of code and beyond in multiple dimensions, including time. Another longtime and important collaborator is Dr. Xu Yang, who is a material scientist who engages in biomimicry in the true definition of the word, looking to natural systems and models in nature, such as the wings of the blue morpho butterfly, the leaves of lotus plants, or the feet of gecko, to explore concepts and topics such as structural color, superhydrophobic and superhydrophilic materials, and so on. And more recently, working with Dr. Dan Lau, who's a biological and environmental engineer here at Cornell University, we have been engaged in exploring programmable matter to consider how design drivers, such as working with synthetic DNA, can actually inform the design and characteristics of materials to limit the amount of energy input to achieve actuation and response. So over the years, we have established a way of working across both the fundamental research and also in the practice work in my studio that frequently starts with the development of tools to model behavior. I like to think of software as a new type of material. We may develop a tool that explores visualizations and simulations of data emanating from collaborators in biology, or it may simply be based on an abstract algorithm. Those tools are then brought into the realm of architectural prototyping to begin to productively contaminate the process with the stuff of making and issues of digital fabrication and emerging technologies. And then finally, moving some of those successful prototypes into questions of buildings and the built environment. So it's a purposefully slow process to work in a rigorous fashion and to meaningfully grapple with the problem of scale. Not all of these systems and models are scalable. So one of the primary questions that informs a lot of our core research is the following: how might architecture respond to issues of ecology and sustainability, whereby buildings behave more like organisms in their built environments? And in turn, what role do humans play in response to these changing conditions? More recently, in building upon a prior project titled eSkin, which I will not go through today, we embarked upon a unique collaboration with the Defect Lab at Arizona State University to innovate the design and engineering of building integrated photovoltaics, so-called BIPVs, through computational design and 3D printing. The title of this project is Sustainable Architecture and Aesthetics, where we're looking at at evolving buildings and their materials to reduce their carbon emissions and better serve people and the planet. As Rachel Armstrong reminds us, the anthropocentric paradigm of resource consumption must shift to resource renewal, circular economies, adaptive reuse, and resiliency. To create highly customized non-standard filters and panels that result in this particular project, in site-specific non-mechanical tracking solar collection systems. The project, Sustainable Architecture and Aesthetics, Emergent Design for High-Performance Solar Panels, is funded by the National Academy of Engineering and the Granger Foundation. We began by looking at biological adaptations, including the heliotropic mechanisms in sunflowers and the light scattering structures in lithopt plants, as non-conventional configurations of panels for designing with light and energy directly, to maximize energy conversion efficiency. Our proposed collaborative approach follows solar path data and omits the typical 50% additional structural metal and 30% copper cable in traditional BIPVs per module, which can significantly decrease the carbon intensity by 15% for the case of an installation in the Southwest. So by working with non-standard componentry and leveraging 3D printing, we're able to design more directly with the dynamics of light conditions throughout a typical day and over seasons and annually. As a result, Agrivoltaic Pavilion demonstrates the first adaptable system with extremely low greenhouse gas emissions, showcasing the potential of sustainable design for resilient land use models to provide an integrated approach to food, energy, and water. And this is an ongoing project. In other projects, we explore non-standard structures and the question, how might we rethink building materials through 3D printing and biologically informed design? In this particular project, Polybrick, we integrate DNA, the mechanics of bone formation, and advances in 3D printing for low-cost and on-demand brick fabrication. This work started over a decade ago when, in the context of Lab Studio, when I was still teaching at Penn before taking a position at Cornell in 2011, we purchased our first powder-based printer to look at the promise of taking some of these data sets emanating from Dr. Peter Lloyd-Jones's lab to explore the possibility of holding data through the development of parametric models of multicellular structures, and then eventually 3D printing those components to contribute to the scientific process, to allow the scientists to project into that data in a new way, and hopefully open up new questions and possibilities. At the same time, I was interested in working with a 3D printer, not as a representational device, but as a way of rapid manufacturing one-to-one scale non-standard parts. And it was during this period of research and prototyping that I began to consider the possibility of another material. In addition to my background in architecture, I have a BFA in ceramics, and prior to working as an educator and as an architectural designer and researcher, I was a practicing artist as a ceramic sculptor and painter. And so I realized that this literal body of knowledge around a single material, in this case clay, could find new applications, new trajectories in a new context. And so what you see here is an image of our first successful 3D printed greenware clay parts. And this was the summer of 2009. And what I simply did was I took out the proprietary media, mixed up a high fire stoneware batch, a powder stoneware, with a bit of maltodextrin and sugar to facilitate the printing process, scrapped the cyanacrylate adhesive and replaced it with a vodka water mix, as informed by some work by Mark Ganter, a mechanical engineer who was developing some similar approaches. And so this just absolutely blew me away, that we could directly print ceramic componentry. And so here you can see the same part printed on the left with the proprietary media, and on the right printed in my clay recipe, bisque fired, so chemically changed to ceramic, and then glaze fired to achieve the final part. Since that time, this has led to a series of seminars and option studios on the topic of digital ceramics, representing over a decade of research, innovation, and teaching. Algorithmic design techniques are integrated with digital fabrication for the production of ceramic components and 3D tiles at a range of scales and applications. In my lab, for the past 5 to 6 years, we've been focusing on the brick as a ground for exploration and research. I felt that this was an interesting and simple point of departure, a way of beginning to engage architectural questions and the possibility of considering how this could move into industry. And so you see here Polybrick 1.0, where we're beginning to explore mortarless connections through age-old means of dovetail joinery, looking at the possibility of hollow bricks, and then more recently in Polybrick 2.0, turning to nature again, and in this case, working with human bone as a set of design drivers to consider the paradox of extremely lightweight and porous, locally fragile, but globally strong, where we could begin to optimize for load conditions and the dynamics of thickening relative to considering how forces travel through geometry and matter. So imagine a wall that's incredibly dense at the base, but it becomes increasingly more porous as you reach the top. And these are some images of current work getting into fine detail of how both the analysis tools, the simulations, and the design drivers that we're extracting as an analog from human bone as a model are applied and informed in the final printed prototypes. What's fascinating about working with human bone as a model is that if we were to take a scan of, say, a person who's a swimmer versus a bicyclist versus a runner, the density of their bone would be very different given the events that impact their body on a daily basis. And so that becomes a really interesting, adaptive, and resilient way to begin to consider how bricks could be informed by the dynamics of forces flowing through geometry and matter. And we're working in collaboration with Dr. Christopher Hernandez, who's a mechanical engineer whose expertise is in the mechanics of bone. More recently with Dr. Dan Lau, who I mentioned just a moment ago, we in Polybrick 3.0 have been looking at the promise of an adaptive and responsive DNA steered glaze. And so what you see here are our first successful prototypes of this. We've actually had a great deal more success than Dan and I originally thought, where we're controlling through a particular DNA sequence fluorescence. And so the first phase is simply to control the emittance of light. And in the second phase, we hope to tweak and design and steer the DNA to respond to particular proteins. So imagine if a wall tiled with Polybrick 2.0 or Polytile 2.0 could respond and give you some cues that your local environment is not safe. And at best, begin to actually clean the local air of particulate matter. So Polytile 2.0 integrates the potential of programmable biofunctionalities in our constructed architectural environments through the development of advanced ceramic biotiles. And what's incredibly exciting about this particular stage of the work is that we're working at scale. So this is a typical 5-inch by 5-inch tile. It's been 3D printed with microtexturing to facilitate the hydrogel that is coated on the substrate, where we're also controlling particular signatures and the fluorescence that you can see here. And then lastly, and this is very recent work, we've begun to really push the microtexturing with these 3D printed ceramic tiles. This particular example informed by the texturing of pitcher plants which are super hydrophobic. So by steering the actual texturing, as you can see here with these dimples, we can control the flow of water. And so here, the same tile is shown at a vertical orientation where you can see those droplets of water are not moving, but staying within those dimples. So imagine a wall that could direct the flow of water based on its patterning at a micro scale to cool a given environment or space, or to direct water for a green wall. So the following video summarizes the polybrick series and where we're at currently. So I'm going to go ahead and play this. The production of ceramic blocks and tiles has a long technological and design history. Ceramic modules of standard measurement have been used as building block in replacement of stone for many centuries. Ceramic bricks and tiles, so ubiquitous in their application in the built environment, have surprisingly lacked recognition as a viable building component in contemporary architecture practice until now. Polybrick, our latest endeavor under the topic of digital ceramics in the Sabin Design Lab at Cornell University, showcases next steps in the integration of complex phenomena. This work includes advances in digital technology, 3D printing, advanced geometry, and material practices in arts, crafts, and design disciplines. The first phase of the Polybrick series features the use of algorithmic design techniques for the digital fabrication and production of non-standard ceramic brick components for the mortarless assembly and installation of the first fully 3D printed and fired ceramic brick componentry. Polybrick 2.0 is generated with the rules, principles, and behavior of human bone formation. This allows for the production of variegated bricks that are light and porous at the top of the wall and dense at the base to carry load and maintain efficient structural integrity, while also amplifying material and formal expressions. Polybrick 3.0 takes our material investigations to the next level. Synthetically designed with advanced bioengineering, these biobricks will exemplify the cutting edge and future of biologically steered clay and ceramic building blocks in architecture. The two prototypes utilize 3D printed clay, hydrogel, and synthetic DNA. As you can see here, a unique ID stamped with DNA in the form of a C for Cornell is fluorescing within the polybrick clay body. Brick stamping has a long history where variegated size, shape, and stamping indicate place, date of construction, and type, and thus serve as invaluable historical documents. With our unique DNA stamps and glaze, we explore the possibility of live signatures and dynamic surface techniques, coupled with non-standard bricks in the context of living matter and digital ceramics. So this work is ongoing in my lab, and if you're interested in taking a deeper dive into any one of these projects, I invite you to visit our lab website, sabinlab.com, where we have a number of published peer-reviewed papers posted there. So the next and last section of my talk explores textile tectonics and adaptive environments. So you can see also through the structure of this talk how scale is being negotiated, starting with materials, considering how those materials respond to particular contextual inputs, then moving into topics pertaining to non-standard componentry and part-to-whole relationships, And then finally, considering adaptive environments. And the following question: how might we design and enhance architecture with the bioarchitecture and behavior of our own bodies and local environments? Can building materials be made more responsive through the integration of artificial intelligence and big data? I'll be talking about two projects that have been developed in my practice. And I should mention, in terms of how we work, the lab is obviously funded differently, primarily funded by the National Science Foundation, which is the largest federal funding entity in the States, as well as other foundations such as the Granger Foundation and occasionally industry partners. And my practice allows me to take on client commissions, exhibitions, permanent architectural projects that are informed by fundamental concepts emanating from the lab, where we have an opportunity to really push them against a brief, questions of site and budget, programming, and so on. Excuse me. So Lumen for MoMA and MoMA PS1 was our winning competition entry in 2017. We were fortunate to win this prestigious competition, which entails the development of a project that is installed in the large courtyard area of MoMA PS1 in Long Island City in New York City. And the success of Lumen, which is by far our largest outdoor responsive architectural intervention, is due to a series of projects that I had developed since 2012, building upon our successful work, exploring how one can design more dynamically with conditions of light and energy through the production of material systems across scales and disciplines, and specifically working with high-tech responsive fibers and exploring fabrication possibilities emanating from the textile industry. And so the first project was a commission from Nike Inc. This was the MyThread Pavilion, which was a part of what they called the Flyknit collective. So in 2012, they were about to launch the Flyknit shoe, which should be familiar to all of you. And as a part of that, they invited 6 designers, architects, and artists from around the world to respond to and be inspired by the core benefits of the Flyknit, including issues of performance, adaptation, lightweight, form-fitting, and so on. And so I proposed to Nike, and my city was New York City, I represented the States, that I wanted to work directly with knitting and digital fabrication processes in knitting, and also to explore how biodata sets collected in this case through a series of workshops with participants could be used as a set of design drivers, not as a representational tool, but to directly link the dynamics of that data to the parameters of the knitted structure. And so the final pavilion was driven by that data. And this was also the first time that I started to work with photoluminescent fibers, as well as solar active fibers that directly engage UV input. In a later project for the Cooper Hewitt, as a part of their 5th design triennial, the Cooper Hewitt Design Museum in New York City, I was interested in building upon the success of the MyThread Pavilion and the particular material systems and threads that I was working with, but instead of tensioning it into a frame, to begin to explore how we could more finely tune the flow of tension forces through this complex and really fascinating material assembly. And so in this case, there was a driving interest in working with the flow of force through geometry and material of the knit as an active datascape or morphology. And at the same time, leveraging over 8 years of deep inquiry in collaboration with Dr. Peter Lloyd-Jones, who I mentioned is a cell molecular biologist, as well as my students and researchers exploring surface design within cellular morphologies, not as a literal application, but as a way of thinking, systemically and relationally, exploring part to whole, how one surface folds into another. And so in this case, we developed a double surface where these individual digitally knit cones that you can see in this image structurally act as springs between the two surfaces. And here you can see the photoluminescent fibers. And I should mention, starting with the Nike project, I began to collaborate with Shima Siki. They're at the forefront of what is called whole garment knitting, which is seamless 3D knitting, so circular CNC knitting. And so you can see the elements of the fabrication and the striation patterns shown here with the photoluminescent fibers being activated. And so in this case, the final experimental prototype pavilion structure developed a reciprocal system where the surface structure is held up by the active bending fiberglass edge and vice versa. And so all of these projects and others really informed our departure for Lumen. And I felt confident that if we were going to be successful in this competition, we really needed to bring forward a material system that was ready to go outdoors, to be explored at altogether different scales, and to really work with the elements directly as an environment. And so I'll just play this video in the background. Turn this down a bit. This video was developed for our proposal and my presentation to the jury. And that year, in 2017, Sean Anderson, who is a curator in architecture at MoMA, was interested in adding to the annual brief for the Young Architects program topics of transformation and materiality, which obviously resonated very much with me. And I was very interested in exploring how the project could operate as an environment over, as an object. And so we developed a full VR model where the jury was able to put on the goggles and really experience the aspects of transformation of the project. The brief calls for a water element, and so there's an integrated misting system that's responsive. We integrated a series of IR sensors that would trip solenoid valves. So the whole misting system really kind of breathed and hissed and changed, and actually was quite functional in cooling down the courtyard area during the hot summer months in Long Island City. The brief also calls for seating and to address issues of sustainability. And so all of the seating elements were composed of recycled spools, essentially, that were formerly used for cable storage. We deconstructed them, CNC'd the tops and bottoms, and in the prototypes, as you just saw, wound and wove photoluminescent microcord around them. I'll go ahead and go to the next imagery here. So here you can see a photograph of the main courtyard, the large courtyard. There are 3 tensegrity towers, each are 42 feet tall, to add a third element of equilibrium to the project. You can see that they have a slight tilt as well. So the entire project was designed to be highly dynamic, both in terms of how the materials respond, but also in terms of how the canopies would take flutter, or the wind was traveling through it, and how the tensegrity towers were integrated as part of the structure. Here you can get a better sense of the plan and organization. We took over the entire courtyard, as well as the smaller courtyards that you can see in the upper portion of the plan. And for me, the most amazing moments were to see how people really took ownership of the project, how they frequented it more than once. They would come during the day, they would come at night. during programmed events. Here you can see a view of the larger canopy with the photoluminescent fibers being activated, and the solar active fibers exhibiting subtle changes of color with these sort of pastel yellows, pinks, and blues. In terms of the fabrication, at that point I had been working with Daisy Fabrics, who is my fabric finisher. And with all of our projects, we frequently start with very advanced digital design trajectories, sort of simple beginnings. And there's always a moment that is incredibly slow and analog. And this is one of those moments. So they work at a 1-to-1 scale. So we literally plot at a 1-to-1 scale pattern drawings that they use for the final finishing and sewing. Some of the details, importantly, we worked with the local site and the matrix of concrete walls to stitch into them, to tension the canopies. And a detail of the webbing, which I'm quite proud of. We've innovated over the years, which is important because the primary tension forces are taken through the net and not necessarily the knit. Here is a view of the misting corridor. So underneath the canopy, you could walk through this and get gently misted. So we ran the whole network of the misting system through the webbing and actually hid that tubing and the detail of the webbing. And then there were feeders or links that would drop down into the cones, and then rings that had a dual function and tensioning the cones or sort of opening them up. And then there were nozzles on each that would then allow for the misting to occur. Just some additional images. Here a photograph of the smaller courtyard, which was one of my favorite moments in the project, I think because of the kind of intimacy of it. And a detail of one of the tensegrity towers. And some fantastic images of the project being occupied. This is on a Saturday during warm-up where PS1 would invite amazing DJs from all over the world to perform, and we would get upwards 5,000 to 7,000 people attending these events, which I have to say I had. I didn't necessarily go to too many of these, but the project held up well, and certainly these images are carry a new meaning in our current context. With the pandemic, I certainly hope that we can find these types of moments of gathering with diverse publics in the not so distant future. And so I'm going to conclude, and I'll go through this briefly with a more recent project, which again builds upon the success of these structures and textile material systems, the collaborations that I've had with Arup, Shimaseki, Daisy Fabrics, and others. And this is a project for Microsoft Research affectionately titled ADA. After Ada Lovelace, I was invited to participate as an artist and designer in residence at Microsoft Research between 2018 and 2019. And so working with researchers and engineers at Microsoft Research, ADA is driven by individual and collective sentiment data collected and housed within the Microsoft Research Building 99 on their home campus in Redmond, Washington, in Washington State. A network of sensors and cameras are located throughout the building, which offer multiple opportunities for visitors and participants to engage, interact with, and drive the project. And this is a diagram just highlighting the material system. You can see how we're bringing back some of the characteristics and organization from the polythread project, which was for the Cooper Hewitt with this double skin, but in a much more refined case here. The data as a set of design drivers include facial patterns, voice tones, and sound, which are then processed by AI algorithms and correlated with sentiment or human emotion. The lightweight pavilion is composed of responsive and data-driven tubular and cellular components held in continuous tension via a 3D printed semi-rigid exoskeleton, which you can see on the left here, They're 3D printed nylon components. The lighting system and materials of the cyber physical architecture respond to human participation, and this is a diagram highlighting the pipeline for how data is fed into the three-tiered lighting system as individual and collective facial pattern data, which are collected through a network of cameras, as I mentioned, then processed by AI algorithms, and that happens in the Azure Microsoft Live data feed. And then we developed the pipeline that would take that data and influence the lighting system, which in turn would allow for the materials to respond, fluoresce, and change color. All of this, in terms of the architecture of the software, is built and designed to be adjustable. We had extensive conversations around the particular sentiment, the terms that we used for that sentiment, and the colors that were attached to that sentiment. And also importantly, the ethical issues in terms of privacy in collecting facial pattern data as a part of a set of the design drivers. Of course, all this data was anonymous. You could opt out if you did not want to participate. Some early renderings of Ada. You can see how it's situated in the atrium. This is a permanent project. It's installed and will be in this home for an indefinite amount of time. And here a detail of the central camera on the interior of the project, which can override all of the other cameras, so you can actually directly drive the project. And one additional thing that we took on with this, I was really interested in taking a deeper dive into fine-tuning the programming of fibers. And so the central tensegrity cone, which you'll get a better view of in a moment, features a skin that is developed with fiber optic cables. And so you can see a detail of those fiber optics, which allowed for a much more refined and nuanced control of the lighting in response to the data feeds. So an important aim of the project was to expand and inspire human engagement. And while artificial intelligence powers the project through the precise narrowing and statistical averaging of data collected from individual and collective facial patterns and voice tones, the architecture of Ada augments emotion through aesthetic experience, thereby opening the range of possible human emotional engagement. And in turn, the project opens new pathways for fundamental research on the use of AI to correlate connections between human sentiment and local environment. And so Ada will be used as a platform for researchers to test their data and machine learning algorithms at Microsoft Research on an ongoing basis. So unlike the pioneering work of Mark Sager, such as his Baby X project, that seeks to humanize AI through more, quote, symbiotic relationships between humans and machines, end quote, Ada does not appear lifelike. Instead, Ada offers subtle and abstract interactions with humans through space, material, and form to augment and expand our emotional range in a specific context, in this case, an office environment. This is a view of that central tensegrity cone, which in turn affects the probable sentiment data being collected as new information. The spaces and environments that we inhabit influence and partially shape who we are and how we are feeling. Through the integration of responsive materials and emerging technologies, Ada hopefully offers an interface for personalizing architecture to explore the possibility of how architecture may be more human and reflexive. And at the same time, Ada expands human emotional engagement through beauty and materiality. It has a capacity to promote and hopefully increase well-being through the direct engagement with the architecture that we inhabit and encounter. I'm going to skip this video because I've, just in the interest of time, you can find this on our website if you're interested in learning more about this project. And just to conclude, this is a photo of some amazing members of my team, both in the lab and the studio, key collaborators. I've been very fortunate to work with some incredible senior designers, collaborators, and students over the years. And also importantly, we've been fortunate to receive funding from federal funding agencies, industry partners, and beyond. And if you're interested in taking a deeper dive into any of the work, you can find us here at jennysabin.com for the practice work, and the sabinlab.com at Cornell for our ongoing research, as well as many peer-reviewed papers that go into great depth on the technical underpinnings of each of these projects, which I've only shared just a few. So with that, I will conclude. Thank you so much for your attention and the opportunity to share the concepts, topics, research, and work that we're developing collaboratively.
Thank you so much for your presentation, and it was extremely interesting. And Cyril, do we have a question on the YouTube Live?
Yeah, it's a small question. It has to do with the purpose of walls and walls or envelope in architecture. And for example, speaking about brick walls, and the question is, there are many functions associated with walls. And for example, if you think about a tree, the role of the stem is to transport the liquid from the roots to the branches, and also to have the structure. And the microstructure is therefore, let's say, designed to this end. And when you take your inspiration for the brick from the bone, how does it combine? Because I don't say that the microstructure of bones, of human bones, for example, is linked with their function. So how do you link the microstructure that you choose with the function that the brick will have afterwards?
Yeah, thank you for the question. So in the case of the research in polybrick based on human bone formation, in the first phase, in terms of function, we've been primarily focusing on how we can harness dynamic thickening of the struts based on the trabecular bone as an analog, right? So as a set of design drivers, so we can more precisely design the polybrick through its network, which is based on ellipsoidal packing, where each strut is dynamically thickened based on the forces that it's having to carry at that particular moment, which is then coordinated across the whole structure. So we've been primarily focusing on the structure and the performance of it, and how we can then steer the density and the shift of, the porosity of these structures, and the kind of paradox of designing with holes, right? You see that everywhere in nature, designing with holes as a way of finely tuning the brick, which has a dual function in the sense that we can begin to consider how bricks and their assembled holes as walls might be more porous, right? Which begins to open up questions of phenomena, the transmission of light, of human perception, and so on. So that's where we're at with that work, and I appreciate the question in terms of the complexity of a wall and what needs to go into the assembly and layers of that wall as a set of material systems. But the way we work is that as we move along, we bring in other contextual questions and inputs that begin to inform the analog. So.
And going on with the brick program, how do you imagine the relation with the envelope of such a brick wall? Because it has its aesthetic in itself. It will be a pity to cover it with something that will impeach you to see it? Yeah.
Yeah, it's a great question. And, in terms of the envelope, we're not there yet, to, be perfectly honest. But I do imagine that it won't be a singular material system. It will definitely involve, other layers that are coordinated and integrated with it. We have started to look at hybridizing the work that we're doing with DNA and the polybrick work based on human bone formation, so that we can begin to think about the skin that meets the elements as being a bit more responsive. So that's been one step that we've taken in starting to think about that layering.
Okay. Thank you. If anyone in the audience wants to ask a question, he should come on the stage. So there's a slight delay in between what we said and what people in the audience can hear. So maybe I can ask a question during that time. You have shown tensegrity towers on the second project you've shown. And what was the material used as a structural material?
Yeah, so the compressive elements are obviously steel. The mast is steel. The base of the towers, and this was done in collaboration with Arup. Clayton Binkley was my engineer, who I've worked with for many years now. There's basically like a web or a wagon wheel of steel struts at the base, which connect to the mast. And then the diagrid is composed of a nylon rope, which was manufactured by a company in the Pacific Northwest that typically make materials for the fishing industry. So that was a really interesting collaboration with the manufacturer. And the erection of the tensegrity towers was, let's just say we incorporated some creative rigging. So we built an easel, a steel easel, and so the mast was resting on that easel. And then as we started to tension the diagrid of rope, the mast started to come off the easel and into place. And so the flying ring also at the top is obviously an important part of that. And everything was designed to be adjustable. There were adjustable U-shaped components at the base of the tensegrity tower. So as things started to settle over time, we could retension the ropes.
Yeah, because you said that nylon, you don't have a problem with creep with nylon?
No, not in the case of this project, which is not permanent. It was up for 4 months, but we developed a tensegrity tower recently for a beach activation project, a public project commissioned by IMCAN in Abu Dhabi, where in that tensegrity tower, the cables are steel. It's it's steel wire rope, which we have to do for a permanent project to address exactly what you just brought up in terms of creep.
Yeah. And well, it looks like no one is daring to come onto the stage. We have an audience which is quite shy in general, I think. But on the last project, maybe I didn't well understood. You said it is data driven, so with the collected data, you have a certain light that comes in and out, if I well understood.
Yeah, so there's a network of cameras located throughout the building, and you can opt in on your laptop if you want to. If you want your facial patterns to be collected day in and day out to give a better sense of your overall kind of well-being and sentiment. So that data is collected through the cameras and then sent to the cloud. an Azure cloud, where AI algorithms process that facial pattern data, including voice tones, and then correlate it with sentiment. So, various states of emotion. That data was then passed into our software pipeline that controlled the lighting, which included PAR lights, an integrated LED system, and the fiber optic cables on the interior. And we coordinated that based on location of data inputs throughout the building. And then that would alter the lighting, which in turn would change the responsivity of the fibers, right? So we had the fiber optic cable fibers, and then the photoluminescent and solar active fibers. So changes in color, changes in how light's being emitted in response to that sentiment input.
Yeah, but so if I'm happy, if I'm smiling, they were color specific, or?
Yeah, so, and we could change that. But what was pretty amazing on the opening night of the project, people realized that if they were on the interior of the project and they sort of like, were angry or, frustrated, they could quickly change how the whole thing was responding. Or if they smiled really big, they could, change the quality of the light and the colors. So that's how it was translated in terms of the overall effects and affects of light and material response, driven by one's direct emotional, input.
Yeah, so that's quite interesting. But we might have to define what is a nice light corresponding to happiness. Maybe it will change depending on your culture.
Exactly, right. And we had many conversations around that, because sentiment is cultural and subjective, and what might be a frown in one culture may indicate happiness in another, right? So, and that's why we designed the whole thing to be highly adjustable. And the research team that I worked with, primarily with Daniel McDuff, who's at Microsoft Research, his research is based on looking at how sort of subtle changes in facial pattern recognition can give us some more clues as to how our environment is impacting our well-being and issues of health, which is pretty amazing to think about how we could then collaborate and integrate that in a more sensitive way with the way that we design and consider materials and quality of light, and so on. So ADA really is it's a demonstrator, it's a prototype of possibilities for that.
Okay, thank you. Is there any other question, Cyril?
No, there is no more question, but I have to say that normally the regular session should have begun right now, so we are running out of time and we have to stop there.
Okay. Okay, so maybe we have to stop. Jenny, the video was on YouTube Live at the same time as being on the stage, and it will be and it's automatically recorded. We maybe should have a little discussion to tell us if you allow or not to be seen directly on YouTube, not on the private one, but globally afterwards.
Right.
So thanks again very much for your presentation, Jenny and Fabian. I think it was extremely interesting. I know we're running really late, but it's not important. We're in France, so we are always late. But nevertheless, we should have had a break of 30 minutes. So now the break is of 0 minutes. And we should, the audience should go directly to either room A or B to watch and discuss the papers of the book and that were available already. on a network, and it's going to be 40 minutes discussion. Let's go to room A and B. Thank you very much.
Thank you.
And you can stay with us if you want. And if we move on a bit out of the map, we can have a private discussion.